guys, welcome to my video. So today I'm going to be working the October-November 2022 question paper 2.2 for physics, and the question paper is 1 hour 15 minutes long, and I'm going to be explaining some of the concepts and how you can be able to answer some of the questions that follow. So please comment, like, share, and subscribe if you like the content, so that I can be able to create more of it. And if you have a specific paper that you'd like me to do, please put it in the comment section so that I can be able to work on it. Okay, so let's begin. So the first question, we've been asked to state what is meant by work done. Okay, so basically, the first question we've been asked to state what is meant by work done. So basically, work done is the product of the force, okay, multiplied by the displacement, okay. So it's the product of the force multiplied by the displacement in the direction of the force, okay, in the direction of the force. So it's very important for you to state that if you have a certain force that you're applying, for example, if you have a particular block and you're applying a certain force in that, but it's also moving in that particular direction, then we say that your work done is the force multiplied by the distance x that we've been moved in that particular direction. That is basically what we mean by work done. Okay, the next one we've been asked to use the answer to A to determine the SI base units of power. Okay, so we know that power, is actually the work done, okay, the work done per unit time. Okay, but we've said that work done is actually force times distance, right, divided by the time, which is an S. Okay, so the units of power, okay, so the units of power will be equivalent to the units of Fs divided by the units of your time. But the units of Fs, the units of F, which is actually work done, is actually mass times acceleration. Okay, so we know that, the units of F, which is actually a force, we know that the force is actually mass times, okay, acceleration, right? And mass is actually in kgs, acceleration is ms to the power of -2. So if we were to put that, that's actually kg ms to the power of -2, okay, multiplied by but we actually know that, you know, displacement is actually m, right? So F is actually m divided by your value of s. So that gives you kg m squared s to the power of -2 divided by s, okay? But this would just be kg m squared s to the power of -3. So whenever you've been asked to determine the SI base units of something, it's always very important for you to state your equations and state the base units of that thing as a result of other things. So what are they looking for? Well, they're basically looking for this equation, right? So basically this equation and all of that working will get you your first mark, and then your answer will get you the next mark. Okay, moving on to the next question. We've been given that the maximum useful output power, P, is given by V cubed B, where V is the maximum speed and B is actually a constant. Okay, so we've been asked to calculate the value of V. Okay, so whenever they ask you to calculate the value of something, best you just make that thing the subject of the formula. So V will actually be P over B, okay, the cube root of that, right? So, but this is actually the cube root of the value of P is actually 84,000, because 84 kilowatts is actually 84,000, because as you can see over here, I've shown you some of the prefixes that you need for AS, and you can see that over here, the kilo is actually times 10 to the power of 3. So 84 kilowatts is actually 84,000 watts, okay? But the value of B is actually 0.56, and that would therefore give you an answer of approximately 53 meters per second. Okay, so your answer is 53. Okay, So basically, what they're looking for is actually just this calculation that gives you first mark, then your answer, which gives you the other mark. Okay, so it's very important for you to be able to just make what you're looking for the subject of the formula and be able to find that out. Okay, so be asked to determine the absolute uncertainty in the value of v itself. Okay, so how do you find this? Well, we know that the uncertainty in v, so let's first find the percentage uncertainty. Why the percentage? Because is you can see over here, I've been given these percentage uncertainties, right? So I can be able to use that to find the percentage uncertainty in v. Then I'll be able to then find the absolute uncertainty. Okay, so delta v over v times 100 percent is actually delta p over p, okay, times 100%, right? So the percentage uncertainty in that plus, okay, delta b over b times 100%, right? But this is actually times 1 over 3, right? Because remember, it's raised to the power of 1 over 3 since it's the cube root of p over b. Okay, where is this coming from? We know that if we have two quantities, and we know that if let's say c is actually, okay, let's say if c is actually a plus b, therefore the uncertainty in c will actually be the uncertainty in a plus the uncertainty in b. Okay, if delta c is equals to a over b, okay, or a times d, then what you add are the fractional uncertainties of these two things. Okay, so it's delta a over a and delta b over b. But the third law actually says that if c is actually a to the power, or maybe a times b to the power of n, this is actually delta a divided by a plus delta b divided by b multiplied by n. Okay, so basically when you raise something to the power of something, you multiply the fractional uncertainties by that power. So if you're actually saying that you have p over b to the power of 1 over 3, okay, so if you have p over b to the power of 1 over 3, something like that, this is actually 1 over 3 times, okay, delta p over delta p plus delta b over delta b. And this is branching off from this fact that actually if you raise something to the power of something, you multiply your fractional uncertainties by that value. Okay, so how do you find then the percentage uncertainty in that? That would therefore be, we have that question, we have 5%. Okay, so it's 5% plus 7%, sorry, plus 7% multiplied by 1 over 3, that gives you 4%. So for you to find delta v, okay, so for you to find delta v, that will actually be 4 over 100 multiplied by 53. Okay, that's about 2 meters. Okay, so that's about 2 meters per second. Okay, okay, that's about 2.12, but we always give it to one significant figure. Okay, so NB, you always give your answer to one significant figure, and our absolute uncertainty becomes 2. Okay, moving on to the next question. We've given a spherical balloon. Okay, this word is very important, I think, because the word spherical actually gives me one formula in mind: 4 over 3 pi r cubed, and this is the formula to find the volume. So I'll just keep this around because it might be used somewhere. Okay, so we've been told that it's filled with a fixed mass of gas, and the small block is connected by a string to the balloon as shown in that figure. Okay, so the block is now held on the ground by external force so that the string is actually vertical. Okay, so the density of the air around it is actually 1.2. So the density of the air over here is actually 1.2. So the air over there actually has a density of 1.2 kgm to the power of -3, right? Then the upthrust acting on the balloon is actually 0.7 newtons. Okay, so the upthrust is actually the one acting up there. Okay, so let's just put it there. So the value of our upthrust is actually 0.071 newtons. So this is very important, we just keep it. So we've been told that the upthrust acting on the string and the block is negligible, so we don't consider anything acting on that. By using Archimedes' principle, calculate the radius r of the balloon. So basically, Archimedes' principle states that the volume of the water displayed is actually equivalent to so the physicist Archimedes came up with Archimedes' principle, popularly known for the Eureka moment. But basically, Archimedes' principle states that if you have an upward buoyant force that is exerted on a body that is immersed in a liquid, then whether it's partially or fully submerged, then that upthrust, that upward force, is actually equal to the weight of the fluid that is displaced by the of the weight that the fluid displays, and it always acts in an upward direction. Okay, so he thought of the upthrust force that actually acts upwards on a particular force. So let's assume you have a particular body that's over there, right? So over here at the top of your body, you exert a certain pressure, P1, and at the bottom here, you exert a certain pressure, P2, right? But we know that the force at A will be greater than the force that would be at B, okay? So the upward force, right, the difference in pressures, so upthrust is basically due to the difference in pressures, right? So upthrust is basically due to the difference in, okay, in pressures, right? But what do we mean by this? So if you look at the pressure at the top, it's actually less than the pressure at the bottom, right? So the bottom here, there's a greater pressure because we have so much water, right? If you consider this as water, we have so much water that is pressing at the bottom as compared to the top. So at the bottom, there's so much pressure than the top, but we know that the force is actually the pressure multiplied by the area, okay? So the pressure will be the difference in pressures, which would just be P2 minus P1 multiplied by your area, okay? But basically, if you're looking at the pressure that will be actually here, we know that pressure is actually H rho G, okay? So H rho G, but this is at 2, subtract H rho G, but this is at 1, multiplied by your area, okay? So we can then factor out rho G, okay, multiplied by H2 minus H1. But remember, this is the density of the water itself multiplied by your area, okay? But look at this. But H2, okay, but H2 subtract H1 is actually, okay, but look at this, okay? But H2 subtract H1. So if this is H2 and this is H1, then the whole height of this object is actually that difference, right? But H2 is just the height of the object that you displace. So it's rho G times H times A, okay? But the area multiplied by the height is actually equivalent to the volume. So this gives us rho GV. So your upthrust will actually be equivalent to your density, the density of what? Of the water. What is your substance in multiplied by G, but this is the volume of the substance, okay? So Archimedes then discovered that's why it's called Archimedes' principle. He discovered that the amount of force that you exert upwards, which is your upthrust force, is related to the volume of water that has been displaced by an object that is partially or fully immersed. So this is the principle that we'll then use to be able to tackle this question, okay? So what does Archimedes' principle say? It says that the upthrust, okay, so Archimedes' principle says that the upthrust is actually rho G multiplied by what? By V, okay? But our upthrust is actually 0.071 times our density is actually the density of the air itself, okay? So the density of our air, which is 1.2 from the question, multiplied by 9.81. But how do you find the volume? Like I've said, it's actually 4 over 3 pi r cubed. So this is actually 4 over 3 pi r cubed. Okay, so how do you find the value of r? The value of r will actually be 0.071 multiplied by 3, okay, divided by 1.2 times 9.81 times 4 pi, the cube root of all of that, right? So our radius therefore just becomes approximately 0.11 meters, right? So that's 0.11. So remember this, right? Ask yourself, what is the Archimedes principle? Okay, how do I use it to calculate the radius? What do I know about the volume? You know what the volume is, and you know how this is going to work. Okay, so you can then be able to find your radius. But guys, I would highly recommend that you break down these calculations. For example, this is a very, very big calculation to just complete all at once. Okay, so this whole calculation is actually very big for you to just complete at once. So I'd highly recommend that you break it down so that you can be able to get it correct. Okay, I'll move on to the next question. We've been given that the total weight of the block is actually 0.053. Okay, the external force holding the block is then removed, right? So that the block is lifted vertically upwards by the balloon. Calculate the acceleration of the block immediately after its release. So what do we know, right? We know that the resultant force is actually mass multiplied by the acceleration. But let us look at our block here, right? So our block is over here, but the force acting upwards, right? The force acting upwards is actually, okay, the upthrust, right? And the force acting downwards is actually the weight, right? But the upthrust is way greater than the weight because the thing is actually moving upwards, right? So this thing is actually accelerating, okay? So it's actually accelerating upwards with a certain acceleration, right? So how do we find that acceleration? We just subtract. What is the resultant force? Your resultant force is actually, well, your upthrust subtract your weight should be equal to your mass multiplied by your acceleration. But to make things easier, let us first calculate our mass. But our mass is actually equivalent to our weight divided by g. What is our weight? It's 0.053, okay, divided by 9.81, divided by 9.81. That gives us a weight of about 5.4 times 10 to the power of -3 kgs. Okay, so what is our upthrust? Our upthrust is actually 0.071. Okay, so upthrust 0.071. Subtract your weight, which is 0.053. This must be equal to your mass, 5.4 times 10 to the power of -3 times your acceleration. So acceleration will just be 0.071 subtract 0.053 divided by your mass, which is 5.4 times 10 to the power of -3. That gives you an acceleration of approximately 3.3 meters per second squared. Okay, so just think of this. Whenever you see the word acceleration, immediately means that there's an upthrust force acting upwards. So always think of that, and the weight force acting down. So how do you find the differences in these two forces? That's your resultant force. Whenever there's an acceleration, there has to be a resultant force. So what is the resultant force? Find the two forces acting and subtract the two forces. Move on to the next question. The balloon continues to lift the block up. The string therefore breaks as the block is moving vertically upwards, right? With a speed of 1.4. So let's try to draw this. Okay, so our balloon is over here and it's lifting this particular block right over there. Okay, so as the block is moving up with a speed, right, of 1.4, okay, so with speed of 1.4 meters per second, right, the string then breaks, right? So the string breaks and the detached block briefly continues moving upwards. Why does it move upwards? Upwards because of inertia. Okay, so it's going to keep on moving upwards because it wants to remain in that state, but it's going to lose all of its energy, or it's going to lose all of its kinetic energy, and it's going to hit a certain maximum height. Then it will start falling down. So as we break this particular thing, it's going to move. Let's assume it's going to move to this particular height, right? At this particular height, its velocity will be equivalent to 0 at that particular point. Okay, and then after it breaks, the detached block continues moving upwards, right, until it reaches that, and then before it then starts to fall vertically down. So after this, it then starts to fall vertically downwards, right, and then it hits the ground with a speed of 3.6. Okay, so as it falls downwards, right, so as it falls downwards, it will then hit the ground. Okay, so here's our block, but it will then hit the ground with a speed, right? So here it will hit the ground with a speed of 3.6, right, meters per second. So the question is said, by considering the motion of the block after the string breaks, calculate the height above the ground when the string breaks. Okay, so I want to find the height above the ground when the spring breaks. Okay, So basically we want to find this height h, right? So from this point, okay, up until that point, we want to find this height h, okay? So this particular height, right? So this height h, that's the height that we want to find. So how do you find this height? Well, the easiest way that you can look at this and be able to understand it, this, okay? So if you assume that this thing is starting at 1.4 meters per second, right? So it's going to continue moving upwards until it reaches 0, right? So it's going to move a certain height that is going to move from this level, okay? So from this level, it's going to move a certain height up until it reaches that other level, okay? So if it's going to move a particular height, right, I can find that height and then subtract it from that total height. So this is actually my h total, right? So I can then find this particular height, right? Then subtract it from that total height. That will give me this height itself, okay? So how do I find that? I know that if I want to find the height from this point up until that point, I'll just use v squared is actually u squared plus 2as, right? So the final will be 0 squared. The initial is actually, okay, 1.40 squared minus 2 times 9.81 times your value of s. So your value of s is actually 1.4 squared divided by 2 times 9.81, which is actually 0.09989. That continues, right? So meaning that the height from that to that is actually 0.09989, something like that. But how do you find the height now from that point at the top to the whole bottom there? We still use the same formula. We still say v squared is actually equivalent to u squared plus 2as, but your final velocity is now 3.6 squared. Your initial is 0 divided by 2 times 9.81. That actually gives you your value of s. So your value of s is actually approximately 0.6605504,587, okay? So your value of your h2 will be the difference between these two heights, will be 0.6605504,587, subtract 0.9989. So that gives you approximately 0.56, okay, meters. So it's 0.56. So what are they looking for? Right, they're basically looking for any expression. So there could be another simpler method of just using that 1.4 is your initial and your final is 3.6. But I'd highly recommend that you try to understand what's happening with this particular system. It's going to rise up, reach a certain height where its velocity is 0. So I find that displacement to reach that height. Then it's going to move from that height until it reaches the ground. So I'm going to then find that displacement from the top to the ground. I subtract the two displacements, then I'll get my height. Very important. So the string breaks at time t is equals to 0, and the block hits the ground at time t is equals to t. Okay, so at time t is equals to 0, it's actually breaking. So this string is actually breaking at t is equals to 0. So during this process, this is actually where t is actually equivalent to 0. But this is actually at 1.4. So if we were to go here, okay, this represents 1.2, 1.4. We plot that point, okay? But at t, it is when it hits the ground, but it hits the ground with a speed of 3.6. So we go on, then we plot our graph, which is actually 3.6. So this is 3, but this is 3.1, 3.2, 3.3. Okay, so this is 3.2, 3.4, 3.6 is somewhere here. Okay, so we're going to have a line that we're going to draw from that point, right, up until it reaches over there, right? So basically, that is going to be okay, so basically we have a line that we're going to draw from that point up until that point. Okay, so basically that is just going to be the line that we're going to be drawing. And I always say with graphs you need three things: your gradient, your lines, your axes, and then you need to also consider your area under the graph. In this case, we're mainly considering plotting the values themselves. The t is equals to 0, it's 1.4, and it's actually in the positive direction, right? So it's in the upward direction when it's actually moving up. That's why it's positive here. Reaches a certain value of 0 to its maximum height, then it starts becoming negative as it begins to fall down. Very important. I'll move on to the next question. We've been asked to state what is meant by the center of gravity of an object. So the center of gravity of an object is actually a point, okay, a point on an object, okay, on an object where all the weight may be assumed, okay, to be acting, right? So it's basically a point where we assume all the weight of an object is actually going to be acting. So that is the center of gravity of an object, okay? So we've been given a uniform beam AB, which is attached by a frictionless hinge to a vertical wall at end A, okay? So the beam is held so that it's horizontal by a metal wire CD. And we're about to calculate the vertical component of the force that is exerted by the wire on the beam, okay? So we have this particular force that is over there, but I can resolve this force, right? So I can resolve this force so that I can be able to find the vertical component of that force, because this force can be resolved into two components, okay? So basically, we have this component here. So that force can basically be resolved into two components. So we basically have this component over here, okay? So if we look at that, we basically have this component over here. Okay, so basically, this force has two components, right? So it has a vertical component, right, that is over here, okay? So a vertical component that is over here, right? And a horizontal component that is over here, right? So we can resolve this force into two components, a vertical component and a horizontal component. As you can see over here from your screen, whenever we resolve a component, we resolve it into the sine component and into the cos component, right? So this is actually 45 sine of 37, right? So that force is actually 45 sine of 37. So we can be able to actually identify what that force actually is. So the vertical component, okay, so the vertical component is actually equivalent to 45, okay? So the vertical component is actually equivalent to 45 sine of 37. That basically gives us 27 newtons, okay? Move on to the next question. We've been asked to take moments about, basically this is point A, and we've been asked to take moments about this point. So moments can act in two ways, right? So we can have a clockwise moment, right, over here, or we can basically have an anti-clockwise moment in that direction, right? So clockwise moment in that direction, then this will be our anti-clockwise in that direction. So how many forces acting downwards? We have that 23 newtons, right, acting down, and that 45 sine 35 acting in the anti-clockwise direction. So the weight also of the block, right, over here is actually acting again in that clockwise direction. So we have two forces in the clockwise and one force in the anti-clockwise. So how do you find the moments? Let's go about it. The summation of the clockwise moments, okay? The summation of the clockwise moments will actually be equivalent to the summation of the anti-clockwise moments, right? So the clockwise moments, remember, we have 23 multiplied by, we need the perpendicular distance from the line of action of the force. So if we were to extend this force, we basically need this distance over here. So we basically need this distance D. But how do you find this distance? Remember, this is a pivot of length 0.96. So basically at its middle, that is where we'll find that particular value. So it's 0.96 divided by 2 plus. Do you have any other clockwise force? We have W, okay? We have W, and that's acting at a distance of 0.76. And how do you find the anti-clockwise? Anti-clockwise, look at the force acting in the anti-clockwise direction. It's 45 sine of 37. So it's 45, okay, sine of 37 multiplied by. But what is the distance from the pivot? It's actually 0.56, okay? So basically, that is 0.56, okay? 0.56. So how do you find the value of W? Well, the value of W would therefore be just 45, okay, sine of 37 multiplied by 0.56. We subtract 23 times that's 0.48. Then we divide by our distance, which is actually 0.76. So that gives us a weight of approximately, I think 5.4 newtons, okay? So weight of approximately 5.4 newtons. So whenever you see a question that asks you to find the moment acting at a particular point. Go to that point, define yourself two things. What is your anti-clockwise moment? State that. What is your anti-clockwise moment? State those and be able to find the resultant. Okay, so the hinge exerts a force on the beam at end A. Calculate the horizontal component of this force. So get this, guys. The summation of forces in the X must be equal to 0. The summation of forces in the Y must be equal to 0 for this thing to be in equilibrium. Okay, so the resultant force in any direction must actually be 0. So let's go to the Y. How many forces do we have in the Y? We have forces acting up and two forces acting down. So basically at A, we're going to need two forces. Okay, so basically at A, we're going to need two forces. One force is going to counteract that force acting upwards. So I'm going to have two forces at A, right? So the other force will be acting upwards, right, to counteract the two forces acting down. And the other force will be acting in that direction to counteract the tension that is acting in the horizontal. So basically at A, we have a resultant force that will be in that direction. That is the force that will be acting at A. But it's made up of two components, the vertical and the horizontal. The whole goal being the forces in the system has to be 0. The total forces have to be 0. Why? Because the beam is in equilibrium. And I've said that if the system is in equilibrium, the summation of the forces in the X and the forces in the Y must be equivalent to 0. So what is the force in the Y? Well, that is actually 45, okay, cos of 37 degrees, right? So that gives me a total of 45 cos of 37. That's actually 36 newtons. Okay, moving on. The block is now placed closer to point D. State whether this change will increase, decrease, or have an effect on the tension in the wire. So basically what's happening here, guys, let's look at our system. So basically what's happening, guys, is this block is actually moved closer to end D, right? So it's saying that the question is saying the block is now placed closer to point D. So the block is basically going to be, let's assume that it's going to be somewhere here. Okay, so this is where our block is now at. But this block is actually causing a clockwise moment, right? So this block is actually causing a clockwise moment in that direction, right? But if I'm going to move it closer to the pivot, what's the change? The distance has decreased. I know that moment, right? I know that my moment is actually my force multiplied by my distance, right? So basically, if this distance is going to decrease, then that moment is also going to decrease. Right? So that's a fact. If you decrease your distance, your moment is also going to decrease, right? So if that block is going to move closer to point D, what's going to happen to the moment is going to decrease. So the total clockwise moment therefore decreases. Okay? So the total clockwise moment is going to decrease. Why? Because W has moved closer to the pivot. It has moved closer to D. So its moment is therefore going to decrease. But also remember, as it moves closer to that, the system has to remain in equilibrium. So what does this tell me about the clockwise forces? Well, it tells me that the anti-clockwise forces, so the anti-clockwise forces are actually also going to decrease. So if the clockwise forces decrease, the anti-clockwise forces also have to decrease so that this whole system is in equilibrium. But what causes the anti-clockwise force? If you look at this, it is this component alone that is causing the anti-clockwise force, right? This component, T sine of theta, that is actually causing that clockwise moment. But if that thing is going to decrease, but we don't change this angle theta, then what has to change? It has to be this tension, right? So this tension has to change in order for the total anti-clockwise moment to decrease. But how does the tension change? Well, the tension decreases, right? So if tension decreases, T sine theta decreases. And if T sine theta decreases, the anti-clockwise force will overall decrease. Hence, the system will remain in equilibrium. So as I move D closer to the pivot, this will actually decrease the tension, right? So this will cause a decrease in the tension. As I move the block away from the pivot, that will actually what? Increase the tension, because the anti-clockwise moment has to increase because the clockwise moment has actually increased. So very important for you to be able to think of that. Move on to the next question. We've been told that the stress in the wire is actually 5.3 times 10 to the power of 7. Now the wire is replaced by a second wire that is a radius 3 times larger than that of the original wire. So we have our first wire over here. Okay, so this is our first wire, right? So this is a wire that has a stress of 5.3 times 10 to the power of 7 pascals. Now we replace it with the second wire that is 3 times the radius, right? So it's something like that is 3 times the radius is that of that wire. So this is 3A, right? So this is basically, if you have a certain radius, so this is on 3R, 3 times that radius, okay? But we've been asked to find the stress in the second wire. So how do you go about this? We know that stress, basically, we know that stress is equivalent to the force divided by the area, okay? So how do you find the area for the first scenario? We basically know that the area, okay, that the area multiplied by stress is basically equivalent to the force that is remaining constant, right? So your area is A, your stress is 5.3 times 10 to the power of 7. That is equivalent to your force, which is your tension. So this tension over here that is acting on this wire, okay, is basically the same tension that is also acting on that wire. So the tension is the same, okay? So we've been asked to find the stress that is in the second wire. So let's go on to find the stress in the second wire. So the stress that is in the second wire is basically the force in the second wire divided by the area, right? But what is the area in the second wire? We know that area is basically pi r squared, meaning that the area is related to the radius squared. So if you were to have the radius 3 times greater, so if your radius is actually 3 times, right, greater, okay, what does this mean about your area? Your area has to be 9 times as great, right, because it's r squared. So area actually changes to 9a. So here it will be your force. What is your force here? It's basically 5.3 times 10 to the power of 7 times a divided by 9 of a. So that gives you about 5.9 times 10 to the power of 6. Okay, so 5.9 times 10 to the power of 6. So think about this, right? Your area is going to change. 3 times the radius, 9 times the area. But the force is still the same. This force is basically the same, but the area has changed. So what's happening to my stress? My stress, therefore, has to decrease because the area is much greater, but you're applying the same force. So your stress needs to change to counteract that force. Okay, so very important for you to be thinking about that. Moving on to question number 4, we've been given a horizontal spring that is fixed at one end. Okay, so a block is then pushed against the other spring and the spring is compressed. Okay, so already this spring is compressed, and from this form I realized that it already possesses elastic, okay, potential energy. Okay, so in this form it already has elastic potential energy, but if the block is released, it accelerates along a horizontal frictionless surface, and the block leaves the spring with a speed of 2.3. So how do you find the kinetic energy of the ball as it leaves the spring? Okay, so we know that the kinetic energy, okay, is actually equivalent to half times m times v squared, right? So very important. Just stating this formula alone will just give you your compensatory mark. Will just give you your compensatory mark. It will give you your C1 mark. Okay. Then you next find your actual kinetic energy, which is half your mass, which is 250, divided by 1000, multiplied by your velocity of 2.3 squared. That gives you a total of approximately 0.66125 to 2SF, that's 0.66 joules, right? 2SF because your mass is 2SF actually, and your speed also is 2SF, so your answer should have 2SF. Then you're about to calculate the compression of the spring immediately after it is released. Okay, so Get this, guys. Okay, so all the elastic potential energy is transferred to kinetic energy. How do you find elastic potential energy? Well, the formula to find elastic potential energy, we know that elastic potential energy is basically the area underneath a graph. Okay, so if you basically have this particular graph that we're dealing with, right? So basically, we know that if we have this particular graph, this is a force, right? So basically, this is a force against, right, extension graph, right? So a force against an extension graph. We know that the area of this graph, okay, so we know that the area of this graph actually represents its elastic potential energy. So if we were to draw a graph like that, we actually know that the area underneath this graph represents the elastic potential energy. So this whole area, okay, actually represents elastic potential energy. So this is elastic potential energy. But to find this area, it's actually 1/2 multiplied by the force. Okay, but to find that area, it's actually 1/2 multiplied by the force multiplied by the extension. But from Hooke's law, we know that force is equivalent to Ke from Hooke's law. Hence, it will be actually 1/2 Ke squared, most popularly known as 1/2 Kx squared. So elastic potential energy is actually 1/2 Kx squared. So if we were to go here, we know that our elastic potential energy is actually 1/2 Kx squared. Just stating this alone, guys, very important for you to state the formulas. Gives you 1 mark. Don't forget to state the formulas if you know them. Okay, but all the EK has been transformed to elastic potential energy. So what is your elastic potential energy? Get this, it's 0.66, okay, 125, and that is actually equivalent to 1/2 Kx squared. Okay, so the value of x is actually the square root of 0.66125 multiplied by 2 divided by 420. So your value of x is actually 0.056. So it's actually 0.056 meters. Okay, so that's your value of x. So just use what the information they've given you. Physics questions are very, very much connected. They rely on information that they've given you. They've already told you that all the elastic potential energy is transferred to the kinetic energy. Always ask yourself, why did they ask me for the kinetic energy in the beginning? Maybe I'll use that later. And you have used it in part B. Okay, so let's go to part C. After leaving the spring, the block moves along the surface until it hits a barrier at a speed of 2.3. Okay, so let's draw this, right? So basically we have something like this. Okay, so this is basically our surface, right? And we have our block, which is something like that, right? So basically that is our block, right? And a block is going to hit a barrier. So it's going to hit this particular barrier, right? But it's going to hit this barrier at a speed of actually 2.3 meters per second, right? But it's going to move away, rebound with a speed of 1.5. But it's going to rebound with a speed of 1.5, right? I'm going to just conventionally say this is my negative direction and this is my positive direction. Whatever way you do it, that will still work, right? So how do I find my change in momentum? I know that my change in momentum, okay, my change in momentum, right, is actually my mass multiplied by my change in velocity, which is actually my mass multiplied by v minus u, okay? But my mass is actually 0.250, right? I already was told that it's a 250 gram block, okay? So my final velocity is 1.5, but in the positive direction, right? So 1.5 in the positive direction, okay? So basically it's, okay, subtract, but this is in the negative direction, which is negative 2.3, okay? So if you punch that in your calculator, that should give you about 0.95 Newton second as your change in momentum. Okay, we've been asked to calculate the average force exerted on the block during the collision itself. Okay, so how do you find the average force? We know that the average force is basically the rate of change of momentum divided by time. The resultant force is actually the rate of change of momentum. What is the rate of change of momentum? 0.95. What time did it take you for that momentum to change? 0.086, 0.086. So that gives you an overall force of about 11.046511, about 11 newtons, right? So basically, that's the force that you need to figure out. So what are the marking points here? The marking points are for you calculating your resultant force. It's only one mark, guys. So the marking point is only for you calculating your particular resultant force, and you'll be able to get your mark. Okay, moving on to the next point. We've been told that the maximum compression, right, is varied in order to vary the kinetic energy. Okay, assume that all the elastic potential energy is always transferred to the kinetic energy. Sketch a graph to show the variation with x of the kinetic energy. So basically, I need an equation to tell me something, right? Whenever you see these graphs, they like these graphs, you just have to think of all the equations that you know, put them down, and determine the graphs that you need. So basically, I know that my EK is equivalent to my EPE based on the information that I've been given, right? So my EK is actually 1/2 kx squared, right? But this is a constant, right? All of this is basically a constant, right? So EK is actually directly proportional to x squared. But this is similar, right? So EK is basically on the y-axis, right? And x squared is basically on the x-axis. So you're basically saying y is directly proportional to x squared. What does the graph of y is directly proportional to x squared look like, right? So I'm going to talk about that now, that if you identify certain scenarios, okay, I'm going to talk about that right now, that if I identify certain scenarios that you need to work out, what do you do with them, okay? So the best graph that I want you to be thinking about is the graph of y is actually equal to x squared, and the graph of y is actually equal to the root of x, right? So the graph of y squared is actually a graph like that, because you know that y is equal to x squared is actually extending to the other side, and the graph of y is equal to root of x squared is actually a graph like that. But we know that this graph also extends into this region like that, right? That region also extends into that region like that. So if you're given these relationships, the graph of y is equal to root of x is actually like that. The graph of y is equal to x squared is actually like that. So based on the equation that you have, you can use these relationships to determine what kind of graph you're going to draw. Since y is proportional to x squared and y is your EP, you then draw a graph like that, right? That would be your correct graph. So it's, okay, so basically something like that, right? So what are they looking for? They're basically looking for a line that has increasing gradient, right? Basically looking for a line with increasing gradient. So the gradient of this line is basically increasing at every different instant, right? Because it keeps on getting steeper and steeper and steeper. If the question has told me that y is directly proportional to the root of x, then I would have chosen that particular variable to work for me. Moving to the next question. We've been told that two progressive sound waves meet to form a stationary wave. Basically, they're asking us for the conditions of a stationary wave. They gave you one condition, they're asking for the other condition. So the other condition is basically that the waves must be traveling, okay? So the waves must travel in opposite direction, okay? In opposite direction, and they must superpose, okay? And they must superpose, or they must meet at a point, right? So you have waves traveling in opposite direction, they meet at the point, have the same amplitude, same wavelength, same frequency, same speed, they form a stationary wave automatically. Okay, moving on to the next question. We've been told that on Fig 5.1, sketch a solid line to show the position of the wave at time t is equals to 0.04. So we're going to be talking about how you can be able to tackle such questions regarding drawing graphs that have been moving. Okay, so basically, if we were to look at this particular wave, we said that the period is 0.016. So what this means is, if let's assume this is your equilibrium position, if your wave is going to move upwards, okay, and reach a certain point that will be there, it's going to take it 0.04 seconds, right? We can also agree that if it's going to move down back, it can also take 0.04 seconds. If it's going to move down in the other direction, again, it's going to take 0.04 seconds. If it's going to move up again, it's going to take 0.04 seconds, okay? So that is basically one period. If you remember a pendulum experiment, as you can see over there, the pendulum moves forward, comes back, and that is one complete oscillation. So basically, that is what we mean when we talk of complete oscillations. It goes forward, then it comes back, and it returns back to where it's supposed to be. That is basically what we mean when we say it's an oscillation. So if we look at this question, we've been told that we're supposed to sketch a solid line that shows the position of the string at time t is equals to 0.4. Like I've said, so at 0.4, if I have a wave that is over here, it has to move somewhere over there, right? If I have a wave that is over there, it has to move somewhere over there. If I have a wave over there, it has to move there. If I have a wave over there, it has to move there, because 0.04 is the time taken for it to move from its maximum to its equilibrium position. Also the time taken to move from the equilibrium to the maximum. So 0.4 is that just one motion itself. If there are 4 of them, like here, if there's 1 here, okay, 2 there, 3 there, and 4 there, that's when it becomes 1 period. If there's only 1 of it, which is 0.04, that's basically going to just be an upward motion. So this is what I call a node. That is a node. So those will remain stationary, but these antinodes will move up in that normal position. So basically, the wave then would therefore be just this wave, okay? Will basically just be that wave, okay? And we'll label this line P. So basically, that is going to be our new wave after we have moved these all points to that equilibrium position. The next one, so you'll be able to get your 1 mark. Then the next one, we've been asked at t is equals to 0.04 seconds. We've been asked to draw again a line, but this time we're going to label it line Q. Okay, so basically we'll go on with our same process. We keep on moving our wave and determine where it's supposed to reach. Okay, so basically let's start with point A. So point A, what's going to happen is it's over here, right? So point A will therefore represent every single point. Okay, so let's try to redraw our wave. Okay, so basically something like that. Okay, so we have point A over there and point C over there, right? So basically if this is point A, and if we were to put an equilibrium position over here, okay, so point A is going to move up towards the equilibrium position, okay? That's going to be 0.04. Then it's going to move up again. That's going to be 0.04. So that's 0.08. Then it's going to move down. That's 0.04. Then it's going to move down again. That's 0.04. So that's about 20. Okay, so that's, sorry, it's about 16, right? So once it's there, then it's going to move up, okay? After it is moved up by 0.04, then it's going to move up again. So this whole point, this whole loop, okay, is going to shift up and it's going to lift and go to that position, okay? So if you're looking at this position, this loop A is going to then move up. So it's going to, since it's already here, it's going to move up 0.04, move down 0.04, move up 0.4, move down 0.04, move up 0.04, and it's going to finally end at this particular position, right? The same with this loop, right? The first thing is going to move down 0.04, move further down 0.04, move up 0.04, up 0.4, 0.4, 0.4, and it's going to end up also at that position, same as C, same as D, right? And this is my new wave, and I'm going to label this wave Q. So basically, whenever you see these questions regarding period that are asking you to sketch the new wave at a different position, just ask yourself, right, what is the position that you're looking at, and what is the new position that you need that wave to be at, and you'll be able to tackle these questions, okay? Very important for you to be thinking of this. Move on to the next question. We've been asked to find, we've been asked to determine the speed of the progressive wave, right? We know that V, okay, is equivalent to F lambda. Okay, so what we need is lambda, and what we need is our F, right? But we already have the value of our F, because F is actually 1 over T, right? Just stating this, you get your first mark. Remember, just stating a formula gives you your first mark already. So V is actually lambda divided by T. So what we need is the value of our lambda. So if we look at this particular wave, right, remember, as I have said, this point right here is a node, actually. So remember, as I have said, this point right here is a node. This point is an antinode. That point, a node. This point, an antinode. A node, antinode, a node, antinode, and a node, all right? So basically, we have a pattern like that. So it's a node, an antinode, a node, an antinode, a node, an antinode, a node, an antinode, and a node. Okay, so basically that's sort of a pattern that we have. But remember, I always say this, right? Whenever we're looking at these things, whenever you have a node to an antinode, that's actually 1/4 lambda, okay, 1/4 of lambda. Whenever you have a node to another node, that's actually half lambda. Whenever you have an antinode to another antinode, that's again half lambda. But if you have a node, a node, a node, this is just basically lambda. Okay, so if we're looking at this particular thing, to move on from here up until you reach here, that's lambda. To move from here up until you reach there, that's another lambda. So basically you have a total of two lambda. So if I'm looking at this, 2 lambda is actually my distance. So if I'm looking at this, 2 lambda is actually equivalent to my distance of 0.80, meaning that my lambda is basically 0.40, right? Essentially, that is my value of my lambda. So my V would just be 0.04 divided by, what is my period? 0.016. So basically 0.016, that gives me a total speed of approximately 25 meters per second, right? So my speed here is 25. Move on to the next question. When given a beam of vertically polarized light, I note incident normally on a polarizing filter, that is its transmission axis at 30 degrees to the vertical. Okay, so we've been shown this particular system and we've been asked to calculate the ratio of I1 as to I naught, right? So guys, I'd highly recommend that you watch my video on Malus's law. I really explain much regarding this concept. It's very helpful if you want to really understand this concept. I've also solved other videos that explain the concept of polarization. So I'd highly recommend that you watch those videos. That will really help you out. But basically, I'm going to try and explain basically what Malus's law is and how Malus's law works. So with Malus's law, the most important thing, okay, so basically this is just Malus's law. Okay, so Malus's law, right? So with Malus's law, the most important thing that you need to know is this formula, guys. I is actually I naught, okay, cos squared of theta. So basically that's the formula that you need to know. And with Malus's law, you just need to know this thing well. What is your transmission axis? What is your angle theta? Basically, this is where things get confusing. But basically, angle theta is you're comparing two sides. You're comparing light that is passed through a polarizer and light before it passed through a polarizer. You're comparing what is my difference in my angles of that light, right? So basically, think about this. If you have vertically polarized light, it's basically light that's vertically polarized like that. Okay, so it's your light that's vertically polarized, something like that. Okay, so the transmission axis of your vertically polarized light is basically something like this. But we've tilted that polarizer 30 degrees to the horizontal. So the new transmission axis, basically something like that. We have tilted it 30 degrees. So that's your angle theta, right? So I1 is basically equivalent to I naught, okay, cos squared of theta, basically. So if you want to find that ratio of I1 is to that, we'll basically say I1, okay, is equivalent to I naught, okay, cos squared of 30 degrees, right? How do you punch cos squared of 30? You're basically saying I naught, right? You open your brackets, then you say cos of 30, you close that, then you say squared, right? So if you punch that on the calculator, that will give you 0.75 I naught, right? But the ratio of I1 over I naught will basically be just 0.75 I naught divided by I naught. So that cancels out. That gives you a ratio of 0.75, okay? So basically that is what you should be looking out for. What is your angle theta and how do you use that angle theta to make your calculations? Very, very important. Moving on to I2. I2 is now after it is passed a second polarizing filter. So again, we need to look at theta, but now it's different. All the light is now polarized in that direction, right? So all the light that is coming in is polarized basically in that direction. So my transmission axis is now a little bit different. So it's more like that. That is basically my new transmission axis. But if you were to look at this, okay, so let's look at that. So your transmission axis is basically something like that, right? But your light is polarized at 90 degrees, so it's something like that, okay? But this angle theta is actually, okay, 60 degrees, right? So if you're comparing the theta between light at 100 degrees, at 90 degrees, and light at 30 degrees, the angle theta will actually be will actually be 60 degrees, okay? So basically very important for you to be thinking about what is your angle theta. So I2 will basically be I1, okay, cos squared of theta. So I2 will basically be I1 cos 60, okay? So I1 cos 60, but all of that squared, that's basically I1 times 0.25. But I1 is basically 0.75 I naught. So I2 over I1 will basically be 0.25 times 0.75 I naught divided by I naught, right? So those two cancel out. We're given 0.25 times 0.75. That gives you an overall answer of 0.1875 to 2SF 0.19. Okay, so 0.19 is your answer. So with Malus' law, it's very easy. Ask yourself, what is your angle theta? And once you have your angle theta, you can then be able to, with Malus' law, it's very important for you to ask yourself, what is your angle theta? Your angle theta is 60 degrees, and how do you use that angle theta to find the new intensity? Very, very, very important, okay? I'll move on to the next question. This is a question on electricity, right? So a question on electricity. We're almost done. We're left with atomic physics, which is our last question, okay? So we've been asked to define electric potential difference. So basically, this is the energy transferred, okay? So this is the energy transferred per unit charge, right? Per unit charge from electrical, okay? From electrical to non-electrical, right? To non-electrical. Some texts might say to other forms, okay? So what do I mean by electric potential difference? I mean, if you have a cell, right? If you have a cell like that, and you connect something like this, as charges move from the cell, they're going to be given some energy from the battery itself. And they're going to move with that energy across the complete loop, and they're going to deposit that energy over to that cell. So that cell, over to that light bulb. So that light bulb is going to take some of that energy, and it's going to dissipate it as heat, right? So it might dissipate it as heat, it might dissipate it as light, but it's just going to relieve some of that energy. Basically, that is how circuits work. They take energy from the cell, then they deposit that energy into a component. But the energy converted from electrical, which is electrical energy basically in this wire, to non-electrical, which can be either heat or it can be light, it can be sound, depending on the kind of component that you have. That is your electric potential difference, okay? The next one, we've been given a battery connected to two resistors, X and Y, and the resistor of X is actually greater than the resistance of Y. And we've been asked to state which resistor dissipates more power. So basically, you need to be able to state the major points. You need to know what exactly are they looking for. Okay, so they're basically looking for about three things, right? So we're going to be working through that, okay? So basically, the current is the same, right? So the current in X, okay, and Y is the same, okay, as they are, okay, in a series connection, right? Okay, so very important for you to be looking at that. So since they're in a series connection, they're basically going to have the same current, right? But think about this, guys. But how do you find power? Power is actually I squared of R, right? So since they're in a series connection, the current flowing through here is the same as the current entering there, and the same as the current entering there, and the same as the current entering there, the same as the current that enters through the battery. Current doesn't branch. If current doesn't branch, it means that it's the same. But Okay, so if we're looking at the power is equal to I squared R, right? But the resistance of X is actually greater than the resistance of Y, right? So we've already been told that the resistance of X is greater than the resistance of Y, right? Therefore, okay, since I is constant, right? So since I is constant, the power is directly proportional to the resistance X, right? And, okay, and since the resistance of X is greater than the resistance of Y, the power dissipated in X will be greater, right? Will be greater, okay? And X, right, dissipates, right, more power. Okay, so whatever they're looking for you stating that the current is basically the same, okay, and stating these relationships. Do you know that power is equal to I squared R? You could also look at it as power is equal to VI. Talk about how the voltage will change and how the power also change. And they also want you to make your overall conclusion, right? So after you have stated that power is equal to I squared R, you can then be able to make your final conclusion. So very important to be thinking about that. Part C, I'm given a battery of EMF 9 volts and internal resistance R connected to resistors P and resistors Q. So basically at this point, this is a parallel connection, right? Why is it parallel? Because these two components are actually there's a junction here for current to branch through, right? So the presence of a junction means current can move in two separate directions, meaning that this is actually a parallel connection, okay? So a total charge of 650 moves through the resistor in a time interval of 540. Why would they give me the time and why would they give me the charge? Well, they might ask me to find the current, right? So let's go. During this time, the resistor P dissipates 4,800 joules of energy and the current in resistor Q is 4.5. Calculate the current in resistor P. So, like I've said, we know that Q is actually equivalent to IT, okay? So the value of I would therefore be equivalent to, okay, Q divided by your value of T, right? What is your value of Q? Basically, that's 650 divided by your time, which is 540. That should give you the current that you'll be looking for of approximately 1.2 amps, right? So basically, approximately 1.2 amperes, right? The potential difference across resistor P. So basically, we know that voltage is actually the work done per unit charge. What work am I doing? 4,800. How much charge do I have? 650. So my voltage will be my work done per unit charge, 4,800 divided by 650. That's about 7.4 volts. So that's about 7.4. Then we asked to find the internal resistance of R. So let's look at this, right? So the internal resistance of R is going to get a certain current I. Okay, so I is going to get a certain current I, but get this, since this is a junction, current is going to branch like that. So as electrons arrive at this point, they have a decision to make. They can either move to P or to Q so that they can be able to give both of them energy. Both of them need energy, really. P needs energy, Q also needs energy. So electrons are going to arrive at the junction, they're going to branch, but the amount of energy that they give to P and Q is going to differ. Whoever has a greater resistance will get a more voltage across them. Again, as current branches, the current is going to be different based again on the resistances themselves, right? So as current arrives here, the current that will be 4.5 is different from the current that is 1.2 over there. But if I have 4.5 and 1.2, and before they basically had to be 4.5 plus 1.2 so that they can branch into 4.5 and 1.2, because Kirchhoff's first law said that current in a circuit can never be destroyed. So the sum of currents entering into a junction is equal to the sum of current leaving that junction. So basically we can't destroy current. So that is what Kirchhoff's law talks about, and being able to understand that law will help you in making the decision on how you can be able to solve this question. So it's very important for you to be thinking of that. So how do you find the internal resistance? We know that the I, okay, across the internal resistance, okay? So the I across the internal resistance is actually equivalent to, okay? So we have 4.5 plus 1.2. So that's basically 5.7 amps, okay? But we know that V is actually equivalent to IR. Therefore, I is actually V divided by R, okay? So, but this is the small letter R, right? So that it's much different, okay? So this is a small letter R, right? So we just want to find this small letter R, okay? So R will actually be V divided by I, okay? So basically we want to find that small letter R, okay? So your R will actually be V divided by your value of I. But what is your value of V? Well, basically from our last question, P gets 7.4. But as electrons arrive here, if they give 7.4 here, they should also give 7.4 there, right? Everything should be fair because this is a parallel connection. They all get the same potential difference, but the current is what is different, okay? So if this takes 7.4, but I had 9 volts to begin with, how much voltage do I have across R? Basically, I'll say my V across R would therefore be just 9.0 subtract 7.4. That would be just 1.6 volts, okay? So my value of R will basically be 1.6 divided by 5.7, right? 0.280707. So basically 0.28 is my value of R. Moving on to the last question. This is particle physics, okay? So this is our last question, and so let's begin. We want to describe the structure of an atom of uranium 238-92. So I need you to understand this, guys. What do you do when the question asks you to describe the structure of an atom? What exactly do they want you to talk about? Basically, an atom is made up of a nucleus, that is protons and neutrons, right? And the atom is made up of what we call electrons that will be orbiting around the nucleus. So when they ask you to describe the structure of an atom, they want to know what is the number of electrons, what is the number of protons, and what is the number of neutrons. Basically, that's what they're looking for in a description of an atom. So what you're going to do, if it has 92, basically when you write these things, it's actually A, Z, and X, right? This is basically the proton number, okay? Also known as the atomic number, okay? And this is basically the mass number, okay? Basically the mass number. That is basically the mass number, also known as the nucleon number. Okay, so very important for you to be able to distinguish that. So if I'm asked to describe the structure of an atom, basically the atom has 92 protons, right? But the neutrons will be 238, subtract 92, which will be 146 neutrons, okay, in the nucleus. Right? And then the last one, I'll be talking of the electrons themselves. It also has 92 orbital electrons, right? So very important for you to be thinking of that. Okay, moving on to our last question. We've been asked for part B, okay, or part B and C. We've been asked for nucleus X to calculate the ratio in C kg to the power of -1 of the charge to mass ratio. So basically, this 238, okay, so this 238 of uranium with 92 is going to form 234-90 of thorium, right? But it has to form something, right? So there's 238, there's a decrease of 4, so there's going to be a 4 there, decrease of 2, so there's going to be a 2 there. But this is actually a helium nucleus, right? So a helium nucleus is made up of 2 protons, and 2 protons have a charge of 2 plus, right? But this is actually a charge of 2e, which is 2 times 1.6 times 10 to the power of -19. So when they say the ratio of charge to mass, they basically just want you to state them the charge. That will give you your first mark. So your charge is basically 2e, which is 2 times 1.6 times 10 to the power of -19. And your mass, right? So since it's made up of 2 protons, okay, 2 protons and 2 neutrons, and all of these have 4u, right? 4 times the atomic mass, right? So one neutron has a mass of 1.66 times 10 to the power of -27. One proton has a mass of 1.66 times 10 to the power of -27. And you can look at this up from your booklet, right, at the beginning. That will give you your formulas. that will be able to give you the value of u. So that's basically for u, which is 4 times 1.66 times 10 to the power of negative 27. So your ratio would just be the ratio of 2 times 1.6 times 10 to the power of negative 19 divided by 4 times 1.66 times 10 to the power of negative 27. That gives you an overall answer of 4.8 times 10 to the power of 7. So that's 4.8 times 10 to the power of 7. Okay, moving on to the last question. We've been given two particles P and Q, which each consist of quarks, and 3 quarks are up, down quarks only. So an up quark basically has a charge of plus 2 over 3e. A down quark has a charge of negative 1 over 3e. So if we want to have a charge of 0, basically we need an up quark, a down quark, and down quark, because this is plus 2 over 3e, this is minus 1 over 3e, that is minus 1 over 3e. And all three of these, right, will add up and give you a total charge of 0, because basically 2 over 3 minus 1 over 3 minus 1 over 3 should be equal to 0. So what we need here, we need an up quark, okay, an up quark, then we need a down quark, then we need a down quark. So basically it's up, down, down, right? Then for particle Q, for it to have a charge of 2e, basically we need an up quark 2 over 3, another up quark 2 over 3, another up quark 2 over 3. So it's up, 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 right? So basically it's up, 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 up. So basically we need all three of those for us to have a charge of plus 2 over 3e. So basically we're done with this paper. It's just a matter of understanding particle physics, the structure of an atom, and working out the situations. Then we had a bit of electricity. We were just asking if you really know about potential difference, what happens in a circuit, and some of the calculations that you need to do. Then we had a question on Malus's law, new addition to our syllabus. And then we had a question on waves in general. Okay, so we had a question just on waves in general, right? Asking about properties of a wave. Do you really know what a stationary wave is and how you can be able to sketch different things? Okay. Then we had a little question about forces, densities, and pressure, as well as deformation of solids, right? So there was a little bit of deformation of solids here and there. Then there was also something about, forces in general, kinetic energy, compression, as well as just sketching graphs in general, right? Then there was also a question on forces, densities, and pressure, especially moments of a force, right? And things like that. And there was also a question on forces, density, and pressure again, but on upthrust mainly, right? This question was mainly on upthrust, and the first one was just, do you know your physical quantities and your units, right? So basically, I hope you enjoyed it. That's the end of my video, and I'll see you in the next one.